Hey guys, welcome back to the channel. Today we are doing calculus again, and we are doing day 2. So yesterday we worked on critical numbers and the first derivative test, and today, as I kind of previewed yesterday, we are going to do points of inflection, concavity, and the second derivative test. It's really cool. It can be a little like messy with your brain first, so I just want to put out a quick disclaimer that when I did this day in school, which was a couple days ago, I was really confused, and then I did the homework and I was still really confused. And so after a couple days, it does kind of just like soak into your brain and you're like, oh, I get it. But if it's not crystal clear, don't worry about it because it will soak in the more that you expose yourself to problems like these. So yeah, I just wanted to put it out there that this one is a little bit mind-bendy just because it feels like a derivative of a derivative of a derivative. It just like gets confusing. But don't worry, it's really quite simple if you can get yourself to not overreact to the idea of it. Yeah, anyways, without further ado, let's get started. Let's talk about my notes here because I think that they're really important. So just about what the different things tell us, because this may sound obvious to you right now. You might want to skip ahead, but don't, because when you start doing problems, you're going to be like, wait, I don't remember what you think tell us. So let's just go back. So f prime x tells us where f of x is positive or negative, right? Remember we were looking at not positive or negative, right? When f of x is increasing or decreasing. And it also tells us relative extrema and plateau points and vertical tangents and all of that, right? F double prime x, on the other hand, is going to tell us about concavity and points of inflection. So let's talk about what those mean. So concavity, I abbreviate because in my class it's allowed, but again, check with the teacher to see if that's like allowed or not. CCU, concave up, or CCD, concave down. So this is the shape, mind you, of f of x. So f prime x is telling you this, but this is about the shape of f of x. So and points of inflection, which we'll get to in a moment. But the idea of both of these is that you need them both as key features for how to graph. So if you were given no information except for the function f of x, you could graph based on f prime x and f double prime x, and you would need both pieces of information. This gives you some of the information that you need, but you already know how to do, and this is going to give you yet more of the information so that by the end, you're going to be able to construct a perfect graph. In fact, we will actually do an example of that at the end of this day. So points of inflection are where concavity changes. So where it would go from like up to like this. Do you see how this is concave one way and this is concave the other way and this is the point of inflection? So this is all of f of x, by the way, this graph. So if this graph of f of x, as we discussed before, you know that these are the critical points. These are what we did, remember, or I don't know, but for the f prime x day, how we discussed how these are like, these flat points are like where the these flat points are where the critical values are, and these can be relative extrema if the sign changes, which obviously in this diagram it does. But this point, on the other hand, is where f double prime x is 0, and this is a point of inflection. So just like these points are to f prime x, so these points are, oh my gosh, I keep forgetting the words. These points are critical values, right? And what it takes to go from a critical value to a relative max or min is having a slope change by it, right? A sign change, right? The same exact thing goes for this. This is a point of inflection because the concavity changes. However, in order to say this, in order to prove basically this is a point of inflection, you would need to say that not only is it a point where f double prime x equals 0, but also where the concavity changes from minus to plus or plus to minus. And only once you've said that can you say that it's a point of inflection. So the designation point of inflection is kind of like the designation relative max or min. You can think about those kind of on the same like hierarchy if you're thinking about like specificity of ability to label something. You can think about relative maximum and minimum and point of inflection. These guys are like on the same thing. I'm going to give them a crown, right? You understand? So these are like both designations that take not only saying that this one takes saying that f double prime x equals 0 and that there's a concavity change, which we'll talk about in a minute. And this one, of course, takes saying that f prime of x is 0 and that there is a sign change, right? So yeah. It's basically what we're going to do today is work on the same process as we did for proving relative extrema for f prime x to show points of inflection for f double prime x. So first of all, let us look at this little example that I've drawn right here. So this is just to sort of understand the idea and so that you can, not be confused from the beginning because it's really easy to get confused here. So this blue is f of x, okay? So if these lines are the tangent lines, I think I sort of talked about this yesterday. This is just for f prime x, where it's the tangent line, right? So what's happening to the slope here? So as you can see, here the slope is going to go from this is a negative number, and then it's going to be a smaller negative number, and then it's actually going to be 0 right here, and then it's going to be a positive number. So the slopes are increasing the entire time. So the slopes of the derivative, mind you. So of course, you can look at f of x and you see that it's not increasing the whole time, but the slopes of the derivative are always increasing, right? The slope of the tangent line are always increasing, right? So that means that f prime x is increasing, right? So then if we talk about the derivative of f prime x, which is of course f double prime x, we know that must always be positive, right? Because when you have a graph, let's go back to just f of x and f prime x. If this is your graph of f of x, then you're going to say that, okay, then you know that f prime x is always positive, right? So this is sort of the same idea, but one level further. So this is saying that if f prime x is increasing the entire time, then the derivative of that must be positive, which should make sense because it's increasing. When you graph derivative, you're graphing the slope. And so if you're saying if this guy is always increasing, then the slope is basically like if the tangent line to something that's always increasing is going to be above 0. It's going to be positive, right? So then similarly, for this one, so this one's concave up. For this one, which is concave down, we're going to look at kind of the same thing. So this is the idea of f of x, and then f prime x follows the slope, which as you can see is sort of steadily decreasing. It goes from a steep positive to flat to a steep negative, right? So it's decreasing. So yeah, so then the derivative of f of x must be f prime x, must be negative because the other one is going down, f prime x is going down. So the derivative is going to be entirely in this sort of bottom region because the derivative, I don't know, this is an example, was doing something like this. In fact, this could be it, right? Because you see it starts positive and then ends up negative, the slope of this. So the slope of the derivative. So it could look something like this. So then f double prime x, as you can see, since that's decreasing the entire time, f double prime x, which maps the slope, is going to be negative the whole time. So that is the idea behind concave up and concave down. There are some other examples which we will go over briefly. So we can quickly talk about this. All this is sort of similar to what we were saying before, and I don't want to dump too much information because that can be what kind of confuses people. So as you can see, this is CCD and this is CCU just by what the graph looks like. So here, f double prime of x is going to be positive. Here, f double prime of x is going to be negative because of the reason we discussed before. Again, you should be able to logic this out. You can memorize it. It's pretty easily memorizable just because the one where f double prime of x is negative is like a sad face, negative things are sad, and the one where f double prime of x is positive is a happy face, happy things are happy. Positive things are happy, right? So that's a pretty easy way if you're going to do like the brute memorization, but I do recommend also conceptually understanding this. So if this is what the graph of f of x looks like, let's remember that f prime x is going to be doing this, which means it's going from steep positive to 0 to steep negative, right? So as we can see, it's decreasing the entire time. So if we were to graph it, the slope though would start up as like steep positive and then go into steep negative. This is not perfect. This is just some vague idea, right? But this would be the graph of f prime x, is going from something positive to something negative. But then we're like, okay, well, what's happening there? What's the slope of that? And then we're like, okay, it's literally negative the entire time. So this would be f double prime x is going to be negative the entire time. So that is a way to conceptually understand why it's negative and the opposite for positive. So this is the point of inflection because it's a change in concavity. It's changing from here, it's changing from f double prime of x being negative to it being positive. And so in that point in the middle, it will be at 0. And remember, a point of inflection, just like the maximum minimums for f prime x, a point of inflection for f double prime x is defined by the fact that here f double prime x is 0 and that before it was one sign and afterwards a different sign, which is what we mean by a change in concavity. So this is another example, kind of a very similar thing, just another example illustrating the point of inflection. Is just to be careful not to make up rules. So of course it is very possible that the first derivative is 0 and the second derivative is 0, as this graph illustrates, but it's also very possible that it's not, as this one does. So for example, f of x were x squared, f prime x is going to be 2x, so f prime 0 is going to be 0, but f double prime x is 2, which is not 0, obviously. So it's just trying to say basically that it's possible for, just because the first derivative is 0, the second could also be, but that is correlation, not causation. It is not necessarily true that the second derivative will be 0 just because the first is at all, as can be shown by, really any of these graphs. But also it's kind of the idea that, like, imagine that you're in a car and you're driving, right? And f prime x is your acceleration and f double prime x is, f prime x is your speed, and double prime x is your acceleration, right? And f of x is your position, but we don't really need to talk about that. So the idea here is that, sorry, that was an awful one of these. I don't even know what these are called. They're really hard to draw. So your speed, and your acceleration, right? So imagine that you're going and you're going and you're going, and then you stop accelerating, and so you let the car start decelerating, right? That would be a change in concavity here, okay? You're stopping accelerating. Instead of your acceleration being positive, your acceleration is now negative because you stop pushing the accelerator, and you start pushing the brake, and you just naturally start slowing down. It's changing from you're no longer positively accelerating, you're now decelerating. But does that mean that your speed is 0? Does that mean that you're stopped? No. So just because, and in the change, in the second between when you're slamming the gas and when you release the gas, there's a moment when f double prime x is 0, when you are not accelerating, but you have not yet begun decelerating. And that is when f double prime x is 0. And that is because the accelerations are changing from positive to negative. That is when you have a point of inflection. But that doesn't mean that f prime x is 0. That doesn't mean that your speed is 0. In fact, your speed is most certainly not 0. So that's sort of a simple analogy that helps me understand why this is true. Okay, we're making a lot of progress. We have exactly 3 more things to cover. We are first going to cover, not this entire example, of course. I'm just sort of going to briefly whiz through it to show you sort of the notational things. The reason I'm going to go relatively quickly through this part is because it is quite similar to yesterday's. So if you understand the f prime x one, you will understand the f double prime x one. And then we're going to do one more thing, which is the actual second derivative test. This is all using second derivatives, but the second derivative test is also important. And then we are going to do one practice problem, which uses the first derivative test and the second. It uses the first derivative. It uses the number lines and the first derivative test, but it doesn't really use second derivative test because I just want to be clear about this right now because this is something I was confused about. The majority of what you do with second derivatives is unique in relation to graphing and is more like this stuff and not actually the second derivative test. The second derivative test gives you the same result as the first derivative test. Like it provides you with the same information. It is just a different, arguably faster way of doing it instead of the first derivative test. But you would not need to do both of those. They're kind of like you could do one or the other. So we will talk about that, but I just want to be super clear that the majority of what you will do with second derivatives and problems is related to stuff like this because this is what's uniquely done with them, or you can do that. But the second, when we do like the big long problem at the end where we're going to graph it, we're going to use the first derivative test and second derivative knowledge as opposed to the second derivative test, but you could also do the entire thing using only second derivatives. I just wanted to be ultra clear about that. So moving right along, let's look at this. So this is entirely of this function over here. We're not going to really talk about this right now, but I guess we are, but we're not going to go into huge detail. So we want to find f prime x and f double prime x. If you were going to graph this, you would do more with f prime x, but we're not going to talk about that right now. We are only using f prime x in this case to find f double prime x. I'm assuming that you all knew how to do derivatives, so I'm not going to go over that. So now we want to set this to 0, right? Because we're looking for the point when it changes concavity. What we want to know here is just like we wanted to know how the slope changed sign for nf prime x yesterday. Now here we want to know where the concavity is changing. So we want to say, okay, if this is going to be equal to 0, it's going to be the point when it changes concavity. Or rather, it's going to be, okay, this might be a little bit dramatic because I didn't technically know this yet. So ignore that. But I don't want to call it critical value because I don't know. I don't want to mislead people, and I don't know if that's technically the right name for it, but these are basically like important points. So we want to set equal to 0. They're basically potential candidates for points of inflection. So we want to set equal to 0. We factor. You all know how to factor. And we end up with x equals 1 and x equals 2. So the same way we did a first derivative number line, we're going to do a second derivative number line. So you just want to do this. This is x, and this is f double prime x. So you want to put your 1 and your 2 and your 0 and your 0. Again, okay, this is another important note. Just as the first derivative could equal 0 or undefined, this one can also equal 0 or undefined for these important points. But of course, since this is a quadratic function, it will never be undefined, so there was no way to test for that. But, I mean, unless it has holes. But yeah, these could also be undefined. So then you want to plug in, again, you're just plugging in points around this. So a point that is smaller than 1, a point that is in between 1 and 2, and a point that is larger than 2. You find the sign, and then because of the sign, you now know this. You now know that it's going to be positive. So as we discussed, if f double prime of x is positive, then f of x is going to look like this. We actually talked about it going the other way. We talked about if f of x looks like this, then because the f prime x is going to go from steeply negative to steeply positive, it's going to look like this, and thus f double prime x is going to be positive. So we talked about it going in that direction, but now that we know that's true, we use it going in the other direction. So we say that if it's positive, it must look like this. Here's going to be a pi because it goes from looking like that to like this. This is another pi, and then it goes back to like this. These are pi's because they're in between these concavity changes. So once that's clear, ignore this. We'll get there. This in purple is very important notationally. Just because this is how you write it. So you would write that f of x is CCU, or if your teacher prefers concave up, whatever, across negative infinity to 0 or 2 to infinity, since f double prime x is positive on those intervals. Then we said the same for concave down, right? Then you can write it like this, or you can write it like this. It's the same thing. So I wrote f of 1 equals 7 is a pi, point of inflection, since f double prime x is 0 at that point. But here's a better way to do it, which is that 1, 7 and 2, 16 are PIs of f of x. And f double prime x has sign changes at x equals 1 and at x equals 2. So why is that important? That f double prime x having a sign change is saying the concavity sign changes, right? Because f double prime x represents the concavity. And f double prime 1 equals 0 and f double prime 2 equals 0. You have to say that. That's really important. Because the point is that it has to equal 0 at that point. This could also, again, say undefined or undefined. And f of x is continuous at x equals 1 and 2 because, of course, if we were using undefined points, it would be important to clarify that it was defined. Okay, let's move on to the second derivative test. So this is saying, let f of x be continuous at x equals c. Then if f prime c is equal to 0 and f double prime c is positive, then there's a relative minimum at x equals c. And if f prime c is 0 and f double prime blah, blah, blah. Okay, so the idea behind this, you can read that obviously if you want to. I don't need to read it out loud. I think that sometimes makes it more confusing. I hate when people read things out loud that are on the slide. Like, I can see too. So I will let you guys read this, but I'm just going to explain it. So the idea is, of course, that if you have a graph like this, obviously there are concavity changes, right, as we could have talked about, where this being a point of inflection, and this going from concave up to, oh my goodness, concave down to concave up, right? But as you can see, there are obviously very obvious relative maximum minimums. And I think that a lot of you guys, when you see this, I'm sure, are like, okay, well, obviously there's got to be a way that you can use f double prime x as concavity change to talk about these minimums and maximums, because the concavity occurs across the minimum and maximum. In fact, the center of the concavity, like the deepest or tallest point of it, is like that. So that actually is true. So if f prime of c is 0, it's saying that if this point is 0, so if f prime x is 0, which is just always something you have to say here to basically show you that it's like flat, and f double prime of c is positive, which means basically in this case that if it's 0 and f double prime of c is positive, so if it's 0 and it's a positive arc, then, sorry, oh my goodness, this is the positive one, I don't know why I keep thinking. If f double prime of c is 0 and if f prime c is 0 and f double prime of c is positive, then there's a minimum, and if it's negative, like this, concave down, then there's a maximum. So that should sort of make sense conceptually. It seems like a much easier jump. So this is an easier jump. You don't have to do as much proving. You don't have to prove. So the thing that's nice about this one is that because you're sort of assuming your readers know what f double prime x is and the implications, you don't need to actually prove that it does change concavity. You only need to plug in. So in that way, it's easier because there's no number line. So this is a derivative test, and it does not involve any number lines. It's sort of just about plugging things in and understanding this logic. This shortcut, one could say. So for this function right here, we'll take the first derivative and we'll take the first derivative points. Here I wrote, could make a number line, but instead let's find second derivative. So this is a really, really important idea. You could solve the exact same problem using a first derivative number line to find the maximum and minimum. But instead we're just going to use these critical values, or what we think are, what we know. We're going to use these critical values. And also we assume continuity across things unless they tell us otherwise, or unless they're very obviously not continuous, but since this is a cubic, it's probably continuous. Unless they were to tell us there's a hole. So you could pick a number line, but we're not going to. Instead, we're going to try it the other way. So the other way to do this is that you find these critical values, and then you're like, okay, f double prime x, going back to this function, f double prime x is going to be negative 12x. Again, we're just taking the derivative of that to get here. So then at x equals 1, we found that point, because we're always talking about these exact points. We're talking, because again, if we go back to the thing I just drew, you have to be talking about these points, right? If you're talking about these points where f prime x is going to be 0. Oh god, that was so messy. Because the whole point is that you're trying to show the maximums and minimums. That's what all of the derivative tests are to do, is to show max and min. To be very clear. Rho. Max and min. So here we would plug in at x equals 1, and we'd say f prime x is negative 12, and x equals negative 1, f double prime x is 12. So then you would say, great, f of 1 equals 8. Where we're getting 8, we're plugging 1 back into this original one, just like we did for the first derivative test. This is what I mean, it's pretty similar. Is a relative maximum. Since f prime of 1 is 0 and f double prime of 1 is negative 12, it's less than 0. So, of course, if it's less than 0, then we know, and it's going to look like this, right? And so if we know that this at 1 is 0, well, or f prime of it is, and then we know that this is a relative max, right? And you should always write using the second derivative test, just because it is more clear, because if you were using the number line, it would be like obvious what you were doing and your logic would follow more. But here, like if you're saying the sign changes, like you're using the exact definition of relative max, but since here you're like not really using that and you're more relying on people's knowledge, when you say this, you should say using the second derivative test. And the same is true for minimums for the first derivative. Same is true for minimums. For if it is for f double prime of x is positive. I do realize now that I lied, and then I told you guys I was going to do a longer problem, and then I actually realized that is on tomorrow's homework. So we will go over that when we go over tomorrow, which is a day all on graphing, which basically combines the day 1 and day 2 skills that we have learned. As a very brief summary of what's important, we learned today about concavity, and we learned about points of inflection and about the second derivative, f double prime of x. And we learned many ways to use that can tell you where the original graph of f of x is concave up or concave down, and where points of inflection are. Remember, points of inflection mean that there has to have been a change in concavity, and the f double prime x is 0. They're kind of the equivalent to maximums or minimums in f prime x. But speaking of maximum minimums, f double prime x can also be used in the second derivative test, where it is used along with the first derivative in order to show the maximums and minimums. So it is used in the way that, you know, if there's something like this, that if this is 0, if f prime x is 0, and if double prime x is going like this, so is concave down, then you can basically prove that this is a maximum. So it can also be used in the second derivative test by that way, along with the first derivative, or it can be used all by itself to basically make comments about the graph of f of x different from the comments you could make only with f prime x. So yeah, that is a summary of what you can do with the second derivative. And once again, if there are any questions or confusions or things that you would like me to clarify, just drop it down and I will of course respond. Thank you guys. I hope you really enjoyed this video and I hope this was interesting. I do think this is a good one to like work through. Like it does kind of, there were moments I bet you could even tell in this video where something really clicked for me or something like I was like kind of confused about still, but it will all smooth out over time. And of course I'll report any big findings or realizations that I have as I'm doing more work. But for now, this is making sense to me, and don't worry if it doesn't to you. It didn't to me. This is my 3rd day working on it. I've done review problems, I've looked at answers, I've done all these things, so don't worry if it doesn't click instantly for you. But I do hope this was helpful. So thank you guys, and please enjoy this little smiley face graphic down here. Have a nice day. Bye, crew.